Well, hello everyone. First of all, I'd like to thank for the organizer for having me here. And I have already experienced how great this community can be. I can tell that this is really a space for all. How many of you like chemistry here in the audience? Quite a few people here. So I will basically follow the logic of this quote throughout my whole presentation. So probably what I am doing and what we were doing is wrong, but some of it might be useful in the future. So amino acids. Amino acids, as we know, basically looking for amino acids is one of the key target for future in situ life detection missions. I'm going to talk more about the practical side of astrobiology rather than the theory that we have heard before. Maybe we can get together after it and find some new solutions for the problems and situations that we've encountered during our experiments. So there are three levels that we have to look at when dealing with amino acids. The first is kind of a qualitative problem. What type of amino acids can we detect and what do those tell us? The second is the abundance of these amino acids. So their ratios, are they more similar to what things that we see here on Earth as the metabolic processes of microbes, or something completely different? And the third is basically what makes it a lot more interesting or puts the icing on the cake is the chirality. As you well know, amino acids are basically chiral, meaning that they have two versions of the same molecule, and they're non-superimposable. Basically, they are mirror images of each other. They have exactly the same amount of atoms, bonds, but they have a totally different structure when we're talking about the isomers. And getting to know the ratio of these amino acids is basically like a smoking gun evidence for life, if you like. But what does it have to do with radiation? Well, as you all know, as we sit here, we are experiencing the effects of radiation. But in the early universe, the activity might have been a lot bigger than it is today. And there are all sorts of theories that are, some of them are quite established, some of them are in the process of proving. But the point is that all the suns and stars basically produce ultraviolet light. And if you have this scattered from the surface, basically you have a polarized light. And basically, amino acids and enantiomers, which absorb specific light better than their counterparts, then basically they get destroyed in the process. This is the same way actually as we detect their ratio, but it's also their doom if we are talking about high intensities. So this is a pretty much established model. We can basically replicate these using all sorts of accelerators and all sorts of sources to basically mimic this effect. The other one is more of a, still about photons, but more of a having the magnetic effect also taken into account when dealing with how radiation affects these molecules. And the third is basically stepping towards particles and subatomic particles, and how they change the isotopic ratio, and through the isotopic ratio, how they change basically the composition of the amino acids and having them change the chirality. So these are just the main theories that we know so far that work. And in our laboratories, we basically set out to mimic some of these effects. At the accelerators at AtomQ, we have three of them, a small, a middle one, and a big one. They are all considered small in the field of nuclear physics. But for our experiments, we basically used a tandem accelerator, which allows a pretty quick change of ion sources. So basically, if you want to irradiate your sample with hydrogen, and then you want to see how the same sample is affected by a heavier ion. Basically, you can change the ions in a matter of hours, or even less if you're experienced. So it has a lot of versatility. That's the point of having a tandem accelerator. On the image, you see probably the closest thing to a real lightsaber. What you see here on the image in the top right is basically how hydrogen ions look like when they're extracted to air from vacuum. And basically, this shows the ionization of the air that the accelerated ions are hitting. So I'm going to jump a bit to chemistry, and you will connect it later. But the point is that we use the technique of capillary electrophoresis to basically see what radiation might have to do with the molecules and their chirality. CE is really a very, very friendly technique, and it's very, very simple. Well, that's what people are basically saying who are expert in the field. But the point is that you have a tiny capillary, a tiny fused silica capillary with an inner diameter, let's say 50 microns, and an outer diameter of, let's say, 400 microns. And when you fill this capillary with an electrolyte and you apply voltage on this system, basically you will see stuff migrate, and they will migrate according to their hydrodynamic volume to charge ratio in this field. So what it allows you to do, it allows you to separate molecules based on their hydrodynamic volume to charge ratio. And if you put a detector in at the specific point of the capillary, basically you can see the molecules migrating through the capillary, and the specific point you get intensity versus time. So you see migrating peaks. This simulation on the left would like to show that, but unfortunately it doesn't run, so you have to believe me that the peaks you're seeing are actually migrating through the detector window that we're looking at. And it is using laser-induced fluorescence. Well, why are we using laser-induced fluorescence? The main reason is that to achieve high sensitivity. You can imagine it like being in a dark room, sleeping, and you basically just open up or open your phone, and you have a lot of bright light coming in, even though if you're doing it in broad daylight, probably you're not affected that much. It allows you to remove background, basically have great big signal. And to do that, you need some molecules that basically have a fluorescent property, meaning that you excited them with a specific wavelength, and they respond to you with a different wavelength. This is a molecule that we used to do the conjugation of our amino acids to basically enhance the selectivity and enhance separation efficiency. So in order to do CE, what you have to do is you have to have molecules that have a net charge other than 0, and we have to make them visible. This molecule here does the two things at the same time. So basically, what you see here is the succinimide from the dye reacting with the amine, forming a stable amide conjugate. And this way, basically, if you separate them, you're getting a pretty huge resolution. So what we did is basically first develop the buffer system or a background electrolyte, the thing that you fill the capillary with to do this separation. It's a pretty simple buffer. It contains 2 components, and the reason behind it was that we had to keep in mind the restrictions that a possible future in situ live detection mission would have. That you're not allowed to have a ton of regions, you're not allowed to have all sorts of mixing to happen. You have to make everything simple. That was the mindset that we had when we were doing the experiments. And as you see, we managed to separate actually 15 amino acids chirally of the 17 that we had in mind. Why is it a promising technique? Just like I said, a few moving parts, no power consumption, easy to implement, and it's just basically very, very friendly technique. And guys at JPL basically are developing this kind of technology. And what you see here on the image is basically the base plate of this whole setup is basically the size of your laptop. Actually, what we did during the irradiations, well, we made some sample holders from a drill press, a kind of a modified drill press, and we made 100 micron thick pellets of racemic alanine, and we irradiated them. Here you see the simulation, how the proton beams would actually behave in a 100 micron thick alanine pellet. And as you see, towards the end, around 80 microns, all the ions stop. And this is actually where the most interesting things happen during an ion beam analysis or irradiation as well, which you see here a bit in more detail. So we have the protons coming in the vacuum from the accelerator, and then we have a window where the protons are extracted to air, and then as they enter the amino acids, they basically lose energy. And the nice thing about the ions is that they give off almost all the energies right before they stop. And this is actually why it's really useful during proton therapy. So we irradiated these samples with these energies and we designed a system to basically stop all the ions in the sample and see how destruction or any alterations occur. So moving forward, basically, you see that this is an expected electropherogram of a DNL, racemic amino acid. Some of you might see that these are not exactly the same height and not exactly the same area. This is just the control that we were using, and we compared all our results to these control runs. So basically, we have two big peaks, and we are happy. And if we go further, we'll be interested more in the small peak part of the electropherograms as we go with the irradiation and as we go as a function of those increases. So what you have here is basically the control that I just showed and different doses that have reached the sample. And it's apparent that some of the peaks are clearly increasing. Some of them show nice correlation. And some of these peaks are basically coming in duplets. And this is what made us think that actually, although we were irradiating racemic alanine, we are basically seeing racemic products. We're still in the process of identifying these molecules and these radicals that we found, but they seem to correlate well with the dose. And also another interesting thing happened when we were looking at the big peaks of the amino acids, and we were just wondering what could this mean. What you see in this picture is basically as we go with the dose, the LD ratio is getting more and more hectic, which means that we're not seeing it going towards one enantiomer or the other, but kind of mixed, noisy version of the two as we go with those higher and higher. So in summary, basically, we put together a simple setup and measured some radicals that could form due to irradiation, and we've done it in a chiral manner to basically see whether our method is capable of separating these chiral amino acids, and more importantly, if we think about the next possible or the most possible places in our solar system where life could be, actually they are in a huge radiation environment. So I think it is really necessary to basically create a library of radicals simulated here in the labs to basically make the work easier and unload this from the scientists who will have to basically figure out how molecules are formed in these high radiation environments and what they are seeing on the results when these instruments send back the data. So basically, we're trying to establish a big library where all sorts of amino acids, mixtures and single ones, are basically irradiated with all sorts of radiation sources, and see what products are there and what can be identified using this technology. So I'd like to thank you very much for your attention.
Okay, we have time for 2 questions for Máté. Chad.
Hi, Chad Pozoriski from Georgia Tech. I was really glad to see CELIF because it's a method that I work with as well, and so seeing it being used around is wonderful. And I have a question about your chiral method, which seemed to work very well. Did you develop this in its entirety, or when did you develop it? Where basically, I want to know all about the chiral method. Is it published? And yeah.
It's not published yet, but we've developed it in collaboration with JPL. Basically, the key thing here is that to do chiral separation, the way you can imagine is that when you have these molecules in a solution and as they migrate through the capillary, if you have some additional additives in your buffer, basically you can emphasize or basically manipulate how these molecules behave. Which I mean that if you have sugars like cyclodextrins, these are circular long oligomers. Basically, these amino acids are, as they migrate, they meet with these cavities, and they basically form an inclusion complex. They go in, they go out, they go in, they go out. And some of the enantiomers are staying longer in this cavity, and some of them are staying for a short period of time. And as they migrate, they basically separate. And this is what we see. And in this context, to basically answer your question, we had a lot of constraints. First of all, we are not allowed to have a ton of additives, a ton of stuff in the buffer, because an instrument has to be able to do this on its own. So we had 2 components in it, which is the HAPIS or HIPIS, I don't know how they say it in English properly, AGPES, and the other one is the MD40, which is basically similar to cyclodextrins, but it consists of sugar oligomers, or actually monomers. And as you go, you have at the beginning 1 sugar, one glucose unit, and as you go 2, 3, 4, etc. And these, after around 7, they start to become helical, and you have longer chains of these sugars, and basically it enhanced the effectiveness of this cavity movement.
Thanks.
Okay, last question.
Hi, my name is Shiva Agrawal from Western Michigan University. So you have used protons for irradiation. Have you considered using leptons?
Not yet. We know it should be done and it should be interesting, but we wanted to use the facility that we have available. And currently, we are only able to do protons and heavy ions. It would be a nice thing to move forward and do all sorts of experiment on this field as well. I'm happy to collaborate.
Second thing is, have you used variable energies for protons? At what energies are you?
In this experiment, we used only 1 energy. We didn't want to have too many variables. It was hard enough to figure out whether, with 100 micron thickness of a pellet, are we able to robustly do experiments. And fortunately, with a simple system and with great care, we were able to basically make it work. So this was the first goal that we wanted to achieve. And of course, we have all sorts of experiments either already running or in plan to vary energies, vary actually the dose rate, which is actually a much more important thing. It looks like it is a key factor in some instances. And also doing everything in vacuum, doing everything. It was in air, but we also would like to do it in vacuum and also in cold temperatures as well.
Thanks a lot.
All right. Thank you very much, Máté.
Thanks very much.